Okay, so hello everyone. Hello everyone. So yeah, so we are going to discuss. Continue our discussion on virtual memory. Uh, so yeah, let's start with a maybe 2-minute recap. So we understand that in virtual memory, the key idea is this: that only a part of the program needs to be in the memory for execution, as and when new parts will be needed. So we will assume that the uh, entire logical space as well as the physical memory is divided into pages or frames. And so it is fine for the process to start execution with only a few pages in memory. As and when there will be a demand for a page which is not in memory, it will be brought to the physical memory from disk. This has to happen transparently to the process. So the OS should not say that you should change code because now we have shifted to demand paging. So that should not be the case. So this should happen transparently. And this happens usually via software means like OS and of course, some modules in the OS, the memory management modules, and the memory management unit, which is usually a hardware unit. So here in this scheme, if the CPU accesses a page that is not currently in the physical memory, it's a page fault. So basically the MMU and the OS has to find a free frame in memory and bring this page for which there is demand into the memory. Now it may happen that there is no free frame in the memory now. Then a victim page or frame has to be selected to replace it. And this is the part that we will focus on in this lecture, how to decide which frame to replace or which page to replace in memory. So basically, there are these two kinds of algorithms that we will study now in detail: page replacement algorithm and frame allocation algorithm. So page replacement is exactly what I said just now. Suppose a new page has to be brought in memory because the CPU has wanted to access that page, but there is no free slot in memory or free frame in memory. So which page should be replaced to swap in this page, the new page which is required? That's page replacement algorithm. And next, the frame allocation algorithm. So how many frames to even allocate to each process? We know that we are in a multi-programming environment, therefore many processes will be sharing the main memory. So how many frames to allocate to each process? Then which frames can be allocated to pages of a process? Is there any restriction and so on? Okay, so this is what we are discussing. We are going to discuss now. Let us start with page replacement algorithms. So we will discuss several page replacement algorithms. Basic motivation is, as I said, there is no free frame in the memory. However, due to demand paging, one page has to be brought to memory. So which page to replace? Now we will discuss several algorithms. So naturally a question comes as to how to compare or evaluate these algorithms. So this is how. So like say if there are many sorting algorithms, how to evaluate them or compare them. Typically we do that by the number of comparisons required. Similarly, here to evaluate or compare page replacement algorithms, we will focus on a particular string of memory references, which is called a reference string. An example is shown below. And then computing how many page faults occurred on that string. So as you see in this, what is written in red at the bottom of this slide, that is a reference string. So it's assumed that the CPU first asks for page 7, then page 0, then page 1, then page 2, and so on. Now, of course, the CPU can demand to access memory from several pages. So 701, 203, and so on. So this is how the CPU is generating addresses. So these pages, so at what is the ideal case? That every time the CPU generates an address, that address is found in memory. However, this is ideal case. This will not happen because we are replacing pages, right? So maybe, so at this point, what I marked here, the CPU generated an address on page 3, but think that just before this, page 3 was replaced. So that would mean a page fault. Or it may happen that 3 is being accessed the first time. So 3 has never been brought from the disk to memory even. So in either case, there will be a page fault. And that is what we are counting. We will tell and we will think a page replacement algorithm to be good if number of page faults is less. So suppose there are two algorithms, A1 and A2. Say A1 gives 4 page faults in this reference string according to this reference string, and algorithm B gives 8 page faults, then we would say algorithm A is much better. Okay, so this is how we will compare between different or compare among different page replacement algorithms by taking the same reference string and then checking how many page faults occurred if this policy or this algorithm is followed. Any questions still here? Okay, if not, let me proceed. The very first and basic page replacement algorithm is FIFO, first in, first out. So basically, suppose I will go through the example, but intuitively, suppose the memory is full and a page needs to be replaced. Replace that page which was first brought in memory. Okay. Okay, Soumitra has a question. Can we consider dirty bit for page replacement algorithm? Yes, you can. But for now, we are not considering that. Okay. So sure, you can consider dirty bit for page replacement algorithms, and some algorithms do that. We will come across such an algorithm, but we will start off with algorithms which do not consider dirty bit. Okay, so as I said, the most basic algorithm, first in, first out. While replacing pages in a memory, replace that page which was brought to memory first. So first in, first out. So assume that this is the reference string shown in this slide, and we have 3 frames. Okay. So first reference was to page 7. So 7 was filled in the memory, then 0, then 1. Then the CPU referenced page 2. See, now there is no free frame in the memory. So 701 are there. The memory is full. So in order to accommodate page 2, one has to be replaced. Which one? According to this scheme, 7 will be replaced because that was the frame, that was the page which was brought the earliest into memory. So among 7, 0 and 1, page 7 was brought the earliest in the memory, and therefore 2 is replacing 7. Right? So, and see, this is a page fault. So because 2 was not there in the memory, this is a page fault, and then 7 will be replaced by 2. Then let's go on. Then the next access is to page 0. It is already in memory, so no page fault. Then access is to page 3. Again, it's a page fault. So one of the pages has to be replaced. Again, which one? See, among 2, 0 and 1, which was brought in the memory earliest? 0. Therefore, 3 will now replace 0. Okay, and so on. So I leave it to you as a task to complete this example mentally, and then you will see that we get 15 page faults in total. And of course, you might say how to track edges of a page, or how to track how edges of pages. Just you can use a FIFO queue. You just need to remember which page was brought before the others, and that has to be replaced. Okay, if any questions, ask, because unless you understand this, the next discussions would be problematic. Okay, if not, then let me ask a question. So you see this reference string with FIFO algorithm and 3 memory frames give 15 page faults. Suppose I give you more page frames. I give you more frames. Is it a guarantee that the number of page faults will decrease? Suppose I give you more frames. So for the same reference string, is there a guarantee that the number of page faults will decrease? Okay. Okay, Soumitra and Ramnivas says yes. But Rahul says page faults may even increase. Why, Rahul? So why are you differing from the others? Can you unmute yourself and say?
Sir, so like if there are four total size of frames, maximum size, the maximum number of frames that could be brought in is four, then it might be possible that every time a page that is being accessed is like different from presently four frames in the memory. So it
Yeah, okay, good. Yes, that is the reason. Such a guarantee cannot be given. So see, okay, again, I'm talking about the FIFO algorithm here. There are some other algorithms which we will discuss which can give this guarantee, but not FIFO. So let's take this example. Again, I leave it to you to work out this, but consider this reference string here. You will see that with 3 frames per process, you will get 9 page faults, and with 4 frames per process, you will get 10 page faults. Okay, I leave this example. I mean, I leave it to you to work this out. But you will see that you will get with 3 frames 9 page faults and with 4 frames 10 page faults. So, and actually with that string, so in this plot, if you plot, x-axis is the number of frames available to the process and y-axis is the number of page faults. You see, it's not a monotonically decreasing curve. Right, so can happen that adding more frames can cause more page faults, depending on the reference string, of course. This is called Beladi's anomaly. Okay, so the Beladi, I think, was the person who first observed this. This is Beladi's anomaly that in the FIFO algorithm, even if you increase number of frames, the page fault can also increase. Okay. Okay, so that was about the FIFO algorithm. Okay, but of course, this is just a basic algorithm. Let's see better algorithms. So, okay, let me just ask one question. So, can you think of something better? So, FIFO has this problem, etc. I mean, so can you think of something better? I think, or I believe that some of you will give some ideas which we will see in the later algorithms. Okay, Shubham is saying LRU or some approximation of it. Or Mukul is also saying the same thing. Yes, exactly. That is towards what we are going. So LRU means least recently used, right? Yeah, so that is what we are going towards, but let's proceed. Okay. Yeah, I thought that you would also guess the same thing, but yeah, let's see. Okay, first step beyond FIFO is counting algorithms. So basically keep a counter of the number of references that have been made to each page. Right, suppose you implement this. So you keep a counter to count the number of references. Okay, then least frequently used algorithm says that replace that page with the smallest count. Idea is that since this page has been accessed the smallest number of times, maybe this page is not much important, therefore replace it. However, most frequently used algorithm is also there, which argues the opposite. Replace that page for which there has been most number of references, because it is assumed that the page with the smallest count was probably just brought in and has yet to be used. Right, so these two are opposite kind of. The LFU algorithm says replace page with the smallest count because possibly it's not important. But MFU says that maybe this page has just been brought in memory, so don't replace it. Rather replace that page which has most number of references already, because probably that page's work is over. I mean, it has been accessed so many times, the process won't need to access it anymore. But again, these are complex algorithms and not much used. Okay, but then we will go towards what is used. But before that, I see a comment by Shomithro. He says that page will be swapped out. That will not be used for long time in future. Okay, Shomithro is saying that page. I mean, I guess he is proposing this, that let's swap out that page, which will not be used for a long time in future. Okay, of course, there is a issue here. Yeah, okay, so that page will be swapped out. That will not be used for a long time in future. Okay. So yes, if that can be done, that would actually be great, because see, that is the crux of it. We want to keep pages in memory which will be accessed in future. So if we can figure out pages which will not be used for a long time in future, that is the best candidate to replace. And that is exactly what is done in this optimal algorithm. Okay. So basically replace the page which will not be used for the longest period of time. So here, see this reference string. Again here, the same reference string. The 2 will replace 7, but this time it's due to a different reason. It is because 7 is that page which will not be used for a long time next. So standing here where 2 is written for the first time, if you think 701, 0 and 1 will be used earlier, but 7 will be used much later in memory. Therefore, 7 is the ideal candidate to replace. Okay, but of course, this is an optimal algorithm, an idealistic algorithm, because it's not practical. We do not know the future memory references. However, this is still useful because often when we have a practical algorithm, we want to compare it with the optimal just to see how good it is or how close to the optimal it is. I mean, sometimes I don't know. I mean, maybe all of you have done basic algorithms course, and I mean, you may have done advanced algorithms courses also. Maybe you have heard of something called approximation algorithms. Okay, so basically the ideal. So we know, suppose what is the ideal solution to a problem, but it is very costly. Maybe it's an NP-hard problem. So then we design an approximation algorithm and we say that, okay, it's like it don't give you the optimal, but you know, the solution this will give will be close enough to the optimal. So it's like that. So this is the optimal algorithm, but it's not practical. So when we discuss practical algorithms, we will compare it with optimal, say. Okay, Soumitra is asking, can we make it as weighted average? So Soumitra, I don't understand the question. Unmute yourself and ask.
Sir, means like in the scheduling, we were some weighted moving average kind of things for means for determining the priority. So can we do it for the pages also?
Weighted average of what?
Sir, of it's being used in the process.
Okay, see, I still don't understand your question, but I would suggest hold on for some time. I think that when we discuss slightly better algorithms, you might actually see what you are going for.
Yes.
I don't fully understand weighted average of what, but just hold on. Maybe in the next 15 minutes, you will get your answer. Okay, Ramnivash is asking, just like MFU and LFU, can't 1 be replaced instead of 7? Sure, I mean, see, you can replace anything according to your algorithm. But see the optimal algorithm. 1 is accessed before 7, right? 1 is accessed twice before 7. So the optimal algorithm should replace 7. If the future is known, that 7 will be accessed much later than 1. So then 7 should be replaced. You can design your own algorithm, fine, but the optimal algorithm will replace 7 because it's assumed that the future is known and 7 is used much later than 1. Fine. So Ramnivash, is this okay? If not, you can unmute and ask. Okay. So yeah, so the optimal algorithm is definitely the best, but it's not practical because the future references are not known. Okay. So then what can we do? So basically, whenever you have to predict the future, the standard is to use the past, right? Even in machine learning, etc., everywhere. If you have to predict the future, the only thing that we can base our decision upon is in the past, and we try to learn from the past. So basically, since optimal is not feasible, use past knowledge. Replace that page which has not been used in the most amount of time in the recent past. Okay. So if a page has not been used frequently in the recent past, we assume that it won't be used for a long time in future. It's just an assumption. It may not be, but yeah, that's an assumption. So one thing we understand that you have to associate the time of last use with each page. So for every page, it should be remembered when the page was accessed last. So again, if we take the reference string, now we use least recently used. So see again here, again see 701 fits in the memory, fine, but then 2 comes, so it has to replace one page. Which one should it replace? It should replace 7 all again, but for a different reason. Now it replaces 7 because 0 and 1 has been used recently, but 7 has not been used recently. Therefore 2 will replace 7. Okay. Then again see 0, the 0 is already in memory. Then 3 comes. Again one page has to be replaced. So which one should it replace? It should replace 1 now because 1 has not been used recently, whereas 2 and 0 has been used after 1. Okay, so now you see we are replacing that page which has not been used recently for the most amount of time. Okay, Shomitra, again, let me proceed for some time. If you still don't get the answer to your question, then you can ask again. So then for the same reference string, if you remember, the optimal gave 9 page faults and the FIFO I think gave 14 or 15 or something like that. Anyway, so here if you use least recent used, you will get 12 page faults, which is better than FIFO but worse than optimal. However, this is a practical algorithm. You do not need to know the future, etc. So therefore, it has been found to be generally good, and this is what is frequently used. Okay, and how to implement it, we will discuss that. So the LRDU algorithm is the most popular, and that is what we will discuss in detail. Just one thing before we start the discussion on implementation of LRDU. So remember Bellardi's anomaly, which we discussed during the FIFO algorithm. LRDU and optimal, these two algorithms do not suffer from Bellardi's anomaly. So these are what are called cases of stack algorithms, and stack algorithms have this property. The set of pages in a memory with n frames is always a subset of the set of pages that would be in the memory with n plus 1 frames. Therefore, it is not possible in these algorithms that you increase the number of frames, but the number of page faults also increases. Okay, so you can look up the literature to know more about this stack algorithms. I'm not going into detail, but then these algorithms which are called stack algorithms, they don't suffer from Bellardi's anomaly. So here it's guaranteed that if you give memory with more frames, then the number of page files will decrease. Okay. Okay, now we will discuss actual implementation of LRDU. But before that, any question? Okay, if not, then let me proceed to LRDU algorithm implementations. So again, since LRDU is a popular algorithm and practical, several implementations have been suggested. One is called counter implementation. Okay, Pankaj is asking, would replacing the least recently updated page be better than least recently used page? Yeah, it's possible, because then if the least recently updated page is replacing the least recently updated page. So here you are making a distinction between read and write. So okay, Pankaj, unmute yourself. Why are you telling this?
Yes, sir. If the page is not updated, then if we are going to replace it, then basically it will only need to write.
Yeah.
It will
So basically,
no need to write.
see again, what you are telling is right, but that is basically you are giving a scheme of minimizing the page fault time. Page fault service time.
Yeah, like I wanted to say that here, if we are going to take some page, say, which is used more frequently but is not updated. And if we are going to replace that,
then you won't have to swap it out.
you won't have to swap it out. Yes, and that will reduce the
page fault servicing time. It won't reduce page faults.
It,
It may or may not reduce page
yeah,
faults.
yeah, but
Okay.
but if it even if we have one more page fault, it will still be that the combined time of both page faults will be less than or equal to the time used for this single page fault.
See again, let me clarify. I agree with what you are saying, but understand that what you are suggesting can help in minimizing page fault servicing time. You cannot guarantee that this scheme will reduce number of page faults.
Sir, if servicing 2 page faults will take less than servicing 1 page fault or equal, then is it not okay?
So that means you are reducing page faults?
No.
That's what I'm saying.
I mean, like, why do we need to? I mean, is it necessary to reduce page fault and not the overall time over a number of page faults?
Both are necessary.
Okay.
So what I'm saying is what you are suggesting is the correct thing, and that can help in reducing the time needed to service a page fault. But you cannot guarantee that doing that will reduce page faults.
Yes, it won't reduce page faults.
It may or may not, depending on the reference string, etc.
Yeah, I mean, it will not guarantee that it will reduce.
Yeah, exactly. So yeah, some variation of that is used. Again, we will see, but you cannot guarantee that that reduces page faults. Yes, the servicing time for a page fault would be reduced, because if you can guarantee that you are replacing a page which has not been updated, then you do not need to swap it out. Okay, so let us so there are different implementations of LRU algorithms. So a simple thing is each page has a counter, and every time page is referenced, the clock is copied to the counter. Therefore, it exactly kept note of that when was this page accessed. Okay, so when a page needs to be changed, look at the counters to find the smallest value. That is the page which has been used least recently. So they replace that. However, the disadvantage is that you actually need to search through the table to find the smallest value. Okay. Another is a stack implementation. So keep the stack of the page numbers in a double linked form. So, I mean, that's the implementation part, but intuitive picture you can see at the bottom. So you're maintaining a stack, and when a page is referenced, you move it to the top of the stack. Right? So basically, so see at this, so following this picture, there are 2 points shown, A and B, and the stack before A and the stack after B is shown. Right? So basically 7 has been accessed in between A and B. So 7 is now put at the top of the stack. So the advantage here is that if you are maintaining this, then you do not need to search for which is the least recently used page. We know that 4 is the least recently used page, the one which is at the bottom of the stack. However, the issue is that a lot of pointer adjustments are needed. So every update will become more expensive, because 7 has to be pulled out from some part of the stack and then pushed at the top. So this will all require, changing pointers and so on. So again, there is a trade-off. In this scheme, finding out the least recently used page is simpler. You don't need to search, but every update is more expensive because a lot of pointers have to be adjusted. Okay. So whatever be it, whether you choose the counter implementation or the stack implementation, LRU needs special hardware, and it is still a bit slow because of these additional operations required. So again, another approximation is a reference bit. This is a very simple approximation. With each page, just associate one bit, which is initially 0. When the page is referenced, set the bit to 1. So when the need for a replacement of a page comes, replace any page with the reference bit 0, if one exists. So you see, this is a very simplified approximation. However, we do not know the order. So basically this is not least recently used in stricter terms of the sense, and in stricter sense of the term. It is basically keeping a very simplistic note of which pages have actually been accessed and which page have not been accessed. And then it chooses to replace one page which has not been accessed, if such one exists. So this bit will remain 0 for a page if it has never been accessed. So if such a page exists in memory, that it exists but has never been used, then this scheme will replace it. But of course, this is too simplistic. So then, building on this idea, you can have additional reference bits. So whatever we discussed in the previous slide using only one bit, now let's say you have multiple bits. You have multiple reference bits associated with each page. So you are recording the reference bits at regular intervals. Let's say we keep 8 bits. Okay. So at regular interval, a timer interrupt causes the OS to shift the reference bit for each page into MSB and shift other bits to the right. Right. So every time. So yeah, I mean, basically now we are bringing in the time factor. So at regular intervals, the OS is shifting the reference bit for every page into MSB and shifting other bits to the right. So basically it's a cyclic clock kind of thing. The reference bit, which is the least significant bit, is brought to MSB and the other bits are shifted to the right. So what does that imply? It implies that if you are using 8 bits like this, then that 8 bits contain history of page reference for the last 8 time periods. In whichever time period it was accessed, there will be a 1 in the bit. The bit value will be 1, and whenever it was not accessed, the bit value will be 0. It's like just like a, I mean, maybe you have done this in maybe digital logic or some kind of similar courses. So basically you are maintaining a counter with a left shift, a right shift operation. So therefore, at any point of time, if you think of the 8 bits, it is basically giving you the history of page references for the last 8 time periods. And therefore the page with the lowest number, considering these 8 bits to be a number, is the LRU page. Okay. So all these implementations are there. Let's discuss another one. So see, there is an algorithm called a second chance algorithm. So here again, you are using only one bit, so one reference bit. If a page has to be replaced, then OK. If a page has to be replaced, then suppose there is a page with reference bit 0, then immediately replace it. If there is a page with reference bit 1, then set the reference bit 0 and this time leave the page in the memory. This is what you have. You are giving it a second chance. Okay, this is what you are giving it a second chance. So next time again, when this page is checked, at that point the reference bit will be found to be 0, and then the page will be replaced. So here you are giving the page a second chance. So understand that the different schemes that we are discussing is having a trade-off between two factors. Factor 1, how closely can you approximate LRU? Or how accurately can you measure LRU? Factor 2, the cost, the hardware cost and the time needed to do the operations. Right. So Tanmay, this is exactly what you are also telling. So in the previous scheme, which we discussed, this one, you are using 8 bits. So you are having a very good approximation of LRU. You are measuring the history for 8 time periods. Great. But then hardware cost is high because 8 bits you are using. Additionally, you have to do a shift operation for every update or for every access to the page. So all this is costly. Whereas if you come to this second chance algorithm, let's say, the cost is very low. You are just using 1 bit and also you're just flipping 1 bit from 0 to 1 or 1 to 0, etc. However, it's an approximation. It's a coarser approximation. You are not being able to keep a very good record of the history. But of course, this kind of trade-off we are seeing throughout the operating system course. And I guess even in networks course, you are saying this. So in any systems course, there will be this trade-off between say accuracy and performance. So there are these different schemes because in some applications, I mean, some computers may think that it is very important to, store the history. So then they might go for 8 bits. But other computers may think, oh, okay, so much of a accurate history is not needed. Therefore, just go ahead with one bit. So that's the trade-off. Also, there is an enhanced second chance algorithm. And this slide will actually connect back to what I think Soumitra asked long back, that can we use the dirty bit, and also what Pankaj was telling. This slide will connect these to these questions. So an enhanced second chance algorithm is improve the second chance algorithm which we discussed by using reference bit and modify bit. So this is basically a dirty bit. I mean, okay, it's written here modify bit, but ideally it should be dirty bit anyway. So here we are checking two things. One is how recently the page was referenced, and second, whether the page has been modified while in memory. So suppose 00. So neither recently used nor modified. This is the best page to replace. 01, not recently used but modified. Well, you can replace it, but then you have to write out before replacement. This is what Pankaj was telling. So definitely best option is 00. 10, recently used but clean. Probably will be again soon, so you should not do it. And 11 is definitely not a question at all of using it. Okay, so this scheme is actually using both the say dirty bit or modify bit and the references. So going back to the discussion I had with Pankaj, both are important to minimize page faults, and therefore that is what we are trying to do using LRU kind of algorithms. And also it is important to minimize the time required to service a page fault. And therefore we would not like to replace a page which has been updated, because then we would have to swap it out. Okay, so both are important. Okay, any questions here? I see one from Soumitra. Can we use heap for storing count? How will be the performance in that case? Okay, Soumitra, what do you mean? Okay, I don't understand. What do you mean use a heap for storing counts? I think you mean some kind of a priority ordering, priority queue kind of thing, by which the least recently used page will be at the top of the queue. Sure, you can, but again, the cost is that you will have to maintain that queue and update the pointers in that queue and so on. Yeah, so heap data structure, if you use, of course, maybe performance will improve because this is the same as stack, right? In the stack scheme that we discussed, we ensured that the the most recently used page is at the top of the stack, and therefore the least recently used page is at the bottom of the stack. Instead of that, you can use a heap or priority queue. But again, the trade-off will be there. Maybe the identifying the least recently used page would be easier or faster, but you will have to do many pointer updates in every reference. Okay, Tanmay is saying, when will reference bit become 0 from 1? In which scheme, Tanmay? This enhanced scheme. This enhanced scheme follows the same rule as this. Or okay. Yeah, as this. So when a page is referenced, bit is set to 1. Initially it's 0, when it's referenced, it's set to 1. Okay, so there is no change in this part. The change is in using the modify or dirty bit along with this reference bit. Okay. Any other questions? Yes, okay, Pankaj, unmute.
So this reference bit in second chance algorithm is similar to like a mutex lock, right? Whenever something is referenced, it will become 1, and whenever we are trying to remove, we make it 0, and if it is still 0 and we again try to remove, basically we replace the page. So can we have it something like
if you are using a second chance algorithm, that can happen?
Yeah, so I want to say that can we further modify it to make the reference bit as let us say a reference number, like reference 3-4 bits, and it is being used as a semaphore, counting semaphore, where for every reference we increase it by 1. And
you started your question, can we further modify it? Answer is yes, you can. You can design your algorithm.
And will it be an improvement, or like
there will be a trade-off? Maybe what you are saying will capture the history more accurately, but then you also understand that. But then you also understand that
1 or 2 bits more. Yeah, like the cost is just 1 or 2 more bits. So any other cost?
This I cannot say. This I have to think.
Oh.
This we have to think. Okay, and Shomitra is asking, in case of demand paging, isn't the bit 1 for every page? Why? Okay, if you are saying a pure demand paging, that means every time a page is brought to memory only if it is accessed. Yes, in case of a pure demand paging, the reference bit should be 1 for every algorithm. But then not all, all demand paging algorithms are not pure demand paging algorithms. Yes, so that's a good point. If you are following a pure demand paging algorithm, that means pages are brought into memory. Pages are never brought into memory without being accessed. Then yes. Yes, Shomitra, unmute.
Sir, if your demand paging is happening, then then such kind of algorithm will not work. Then
yes, it won't work. Then there is no point in. So if the system is such that reference bit is 1 for every page, then there is no point in using this algorithm.
Yes.
Then you have to use some scheme which just figures out the history. Any other question? Okay, in the interest of time, let me proceed. So if you remember, we started discussing that there are 2 kinds of algorithms. The page replacement algorithm, which we discussed, and the other one is simpler, frame allocation algorithms. So basically, which frames can be allocated to a process, or how many frames can be allocated to a process. Remember, it's a multi-programming environment. Therefore, many processes want to use the memory. So how many frames to allocate to a process? So here there can be several, this is much simpler. Here there can be several system constraints. Like say each process needs a minimum number of frames. Let's say in IBM 370, for some reason, it was kind of decided that every process would need at least 6 pages. And of course, maximum is the total frames in the system. Now it has to be somewhere in between. So now there are 2 major allocation schemes, fixed allocation and priority allocation. And of course, there are many variations which we won't discuss. But let's just discuss the simple fixed allocation and priority allocation. This is very simple. Fixed allocation is equal allocation. So let's say there are 103 frames. After allocating frames from the OS, there are 103 frames and 2 processes. So give every process 51 frames. So that would be 102, and 1 frame is kept in the free frame buffer pool. If you remember, I think a couple of classes back, we discussed the need for a free frame buffer pool, because when a process, maybe there's a copy on write kind of mechanism, the page needs to be quickly available, then this free frame buffer pool is used. Right? So anyway, this is a very simple allocation. So basically, allocate. Okay, so this is equal allocation. And the proportional allocation is that allocate according to the size of the process. So of course, here you have to, the system has to have some idea, a priori idea of the process size. So how large is this process likely to be? So based on that, it can allocate proportionally. So the total size is this S, capital S. So every process is allocated in proportion of its size, where the normalizing factor is this total size of all processes. So it's very simple. Okay. So this is fixed allocation, and priority allocation, again, we assumes that every process has an associated priority. So instead of size of processes, now you are considering explicit priorities. Now, of course, you might say that size was also a priority, kind of priority. Like you might say larger processes we give more memory. But then basically here you are considering instead of size some other kind of priority. So let's say the scheme may be such that if process PI generates a page fault, then either one of its own frames has to be replaced or select for replacement a frame from a process with lower priority than PI. So you say that, okay, PI needs a memory, sorry, PI needs an additional page. So which process should be penalized? Or I should not say penalized, but then you have to, remove one page from some process. Either it has to be PI itself or some, lower priority process than PI. So here that comes to an interesting question. Global versus local allocation. The question is this. Suppose a particular process, say PI, has a page fault. So it needs a new page. So and say, let's say one page has to be replaced. Which page can be replaced? Does it have to be a page of that same process for which a new page is needed? Or can it be that because process PI had a page fault, the OS replaces some page of process PJ? Okay. So the question is, if some process PI needs a new page in memory, will a page of the same process only be replaced, or can pages of other processes also be replaced? So the global replacement scheme says that select a replacement frame from the set of all frames. That means if to service a page fault of process PI, the OS can choose some other process PJ and take one page from it. So this gives greater throughput. So this is what is used more commonly. However, this also means that process execution time can vary greatly, since a process cannot control its own page fault rate. Maybe you have written your code very carefully so that there is no page fault, maybe, let's say. But then because some other process has got a page fault, OS can replace a page from your process. So you cannot actually control how many page faults your process will have. And the other scheme is local replacement. This is that each process selects from only its own set of allocated frames. That means if process PI has a page fault, one page from process PI itself will be replaced. So this has concerns like underutilized memory and so on. However, it's more consistent per process performance. That means every process can actually, control how many pages, how many page faults it will have, because it exactly knows how many pages it has in memory and so on. Okay, I'll stop here today. If you have any questions, then ask. So we discussed page replacement algorithms and frame allocation algorithms. Pankaj is saying in local version, a process may need more than the max at once too, right? Max means what? Unmute yourself and ask, Pankaj.
Sir, by max, I mean all the current frames of the process. So we said we are going to replace one of its own.
No, so clearly in the local replacement scheme, every process is allocated a fixed number of frames and cannot ask for more.
So we basically restrain how much memory a process can use or number of frames.
Yeah.
Sir, had two doubts from the start of the virtual memory thing, that when we are saying we'll store invalid frames on disk, we only mean the swap space, right?
Invalid frames? What invalid frames?
The invalid frames, we are storing by invalid, I mean the inactive frames.
Oh, the bit, the valid invalid bit.
Yeah.
Yeah, so what's your question?
So we are storing all those invalid ones only in the disk, we said, right? So
yeah,
the disk is only the swap space or the entire disk?
The subspace. The subspace is a part of the disk which is specially reserved for these.
Yeah, so that swap space is generally only like twice the size of main memory, right? So when we say we got a huge amount of virtual memory, it is only like only 2 times more we got, right? In general.
Yeah, in general it is so, because again, see, it cannot be unlimited, right? But of course, if for some system it is thought that there can be a lot of subspace, then you can increase it. I mean, that's just a guideline because that is what is found to be working well for PCs. But this I'm not sure. Maybe servers have more subspace, where it is known that many more processors will be used. That subspace being twice the size of memory is a guideline specifically for PCs.
Yes. One more thing, sir. So when we are getting all this increased virtual memory, all this the combined size of all the page tables will also be increasing by the similar factor to how much we got more virtual memory compared to the physical memory. So storing all that will also basically the combined size of all these page tables will also be a lot. So is it not a waste of memory storing all of them in the main memory in this way?
So where do you want to store them?
I mean that I'm just asking if basically don't want to use the scheme instead.
Sorry.
Just
Okay,
asking if
so
it is
you
a
don't
drawback
want
in
to
virtual
use
memory scheme.
Okay.
I mean,
So
not
see again.
not using, but is it a kind of defect or negative side of virtual memory?
Yes, page tables can become huge, and we have dedicated one whole lecture for that, hierarchical page tables and so on.
Yeah,
Therefore,
but we are
definitely page tables becoming large is a issue.
Yeah, and now we basically tripled all the page tables, so it is becoming an even bigger problem.
We tripled all page tables means?
Initially, our page tables were restrained by the size of physical memory, but now they're restrained by the size of virtual memory, which is just now we said that for a general PC it is about 3 times because of swap space size.
Okay, go on.
So since the virtual memory is basically 3 times of physical memory, now it will be restrained by the virtual memory, which is kind of similar to saying that the table sizes are restrained based on like thrice or 4 times of the physical memory. So overall, we are increasing the sizes by around that much factor, right?
Yeah, page table size are increasing. And why is that happening?
Why is that happening? Because we decided to basically the swap space, because the swap space will.
No, forget the swap. So it seems you have a problem with the whole virtual memory thing, because page tables are increasing, and what you are saying is right. But why did we go towards this?
Why did we go towards this?
This whole scheme, why did we go towards that? This whole virtual memory and so on.
Because we wanted to swap the things, basically storing the
wait.
memories.
We went towards this virtual memory scheme because we want to swap pages in and out.
I think that's
a completely wrong answer, because it's overhead. No one goes to a more complicated scheme because we want to increase overhead.
Not overhead. I mean, because we can swap, so we can run more processes simultaneously in the main memory.
Yes, and that's one thing. So we can run more processes. Second reason. Second reason is that processors nowadays are demanding more and more memory.
Yeah, they are very big.
Yeah. So given these needs, you have to pay some cost, right? You want a bigger car, you have to pay a bigger cost. You want to upgrade from a bicycle to a bike, and you say I won't give any extra cost, and that's not practical, right?
So these tables are again stored, basically again tableized. No, again that will go to hierarchical scheme.
May go. That's what we discussed.
Yes.
We also discussed that multi-level page tables has its own problems because it also slows down the whole process. Therefore, people may go for inverted page tables or some other things. But then ultimately, page tables becoming larger is the cost that you have to pay because we want more processes. We want every process to have more memory and so on.
Yes, sir.
Fine. OK, let's end this class. Thank you. We'll continue tomorrow.